everyone. My name is André. I'm a PhD student at UF's Department of Chemistry. I study non-thermal plasma. I see we gathered quite a crowd. I thank everyone to come to see my presentation. And now let's begin because we have little time and much to cover. So I will present my work, which is the sulfur functionalization of graphene by non-thermal plasma. So let's begin talking about graphene. Graphene is basically carbon in a thin 2D honeycomb lattice, which is illustrated here in electron microscopy. And it has many remarkable properties such as high electrical heat conductivity, high surface area, and due to its many interesting properties, it has many different applications. And some ways of increasing the applications is to functionalize. And so you can insert heteroatoms into graphene to modify its properties, and some of the elements inserted are oxygen, nitrogen, hydrogen, boron, sulfur, phosphorus, and others. And graphene has a characteristic that its edges and defects are more reactive for insertion than the basal plane. And some effects that the insertion of these elements causes is turning graphene into a semiconductor, both P and N type. It can change its absorption properties, availability, catalysis. It can sense many different analytes, and it can generally change its bonding to different substrates, which is interesting for composites. And one of the elements you can insert is sulfur, which is interesting because it is less explored than, for example, nitrogen or oxygen. And it has been inserted using thermal annealing, in which you heat graphene with a source of sulfur. You can attack its edges with electrophilic substitution. You can generate radicals with many metals, which will also attack the edges. You can use plasma. There's simultaneous reduction and insertion, and the main functional groups of sulfur are thiol and sulfonic acid. And so the function of the thiols is enabling further modification via click chemistry reactions, which are very explored. And it can also interact with many heavy metals such as gold, mercury, cadmium, which can be used to sense and to absorb them to remove from a contaminated site. And the sulfonic acid, which is strongly acidic, and so it easily deprotonates to an anion, giving negative charge to the graphene, which increases wettability and dispersion. Some of the applications of sulfur-modified graphene are sensing and absorption of heavy metals, evolution of hydrogen and oxygen, modified electrodes for voltammetry, catalysts, semiconductors, medical applications. There are many. And now let's talk a little about non-thermal plasma. Many people already talked about it. And for us, it is a source of reactive species, such as free electrons, ions, radicals, excited species, ultraviolet photons, and etc. And it is widely used for many applications, as we saw the entire event, including surface modification. And some effects on the surfaces include cleaning, in which you remove some contamination that is present in the air from the surface. After that occurs etching, in which you remove material from the surface via impacts. And depending on the gas you use to produce your plasma, the atoms in the gas can bond to the surface, which is known as graphene. And if you have oxygen, you can oxidize the surface, among many other effects. And now, why use non-thermal plasma with a liquid phase? So, gas phase MTP, it has a characteristic which acts only at the surface. It has low penetration. It can be an advantage or a disadvantage depending on what you want to do. For treating powders such as graphene, if you have a clump of powder, it won't reach all the surfaces, leading to inhomogeneity. And to remedy this, they spread the powder to a film which leads to low treated mass. But if you put your graphene on a liquid like this, and you stir it, it will lead to a cycling of the graphene on the surface, which leads to a more homogeneous exposure. You can put more mass to treat. It is easy to integrate into production, but principally you have another phase which will give another degree of complexity to the chemistry, which is very interesting to explore, and also the equipment is cheaper. To produce this plasma, for example, you need fancy equipment such as vacuum pumps, pulsed sources, and etc. But to produce this reactor, which is a picture of mine, you can literally produce it with any junk you find in the street. To cite the Iron Man film, you could make a reactor inside a cave. And so, the sulfur modification of graphene by non-thermal plasma. It has been used to insert sulfur into graphene, and many works use vacuum methods, which we have those issues that I already talked about. And they also use a lot of graphene oxide, which is easier to functionalize due to more defects and etc. And few works treated graphene in liquid phase with plasma, and also fewer use pristine graphene. And so the objective of the work is to insert sulfur into graphene using a hybrid gas liquid non-thermal plasma, and to characterize the modification and the process. Now for my results. First, let's talk about how I do the process. So here we have a drawing of my system. It is basically a cylindrical flask with a water jacket for temperature control. It has a magnetic steering. I inject gas that comes from a tube inside it, which is argon. And we have a high voltage source, which is connected to two electrodes, one inside of the solution and one above the liquid surface, which discharges, generating the plasma. And the graphene I utilized is a commercial sample 2TM XP graphene, which has a very high quality, 1.5 micrometers average size, more than 95% of carbon content. And I used as a sulfur source potassium thiocyanate dissolved into the water, and the material I obtained is more easily dispersed in water, and it has a very good adhesion to gold. So for the FTIR, we can see that the spectra are essentially the same. The bands are very, very similar, so that indicates that the MTP treatment doesn't degrade the structure. For example, if it oxidizes the graphene, those bands such as carbonyls will increase, but it is the same. But if you zoom in the fingerprint region, we can see that those peaks, they are shifted by 4 centimeters minus 1. I checked them all. And there's one peak that doesn't obey this, and it's new. They attribute it to carbon sulfur at 637 centimeters minus 1. There are other works with inserted sulfur into graphene that saw similar peaks in similar regions, so I attributed it like that. And I used graphene to assess the degree of order of the samples. Here we have the two bags that I used. This one corresponds to sp2 carbons, and this one corresponds to disorder. If I divide this one by this one, I get a ratio which the smaller it is, the higher degree of order. I measured it in triplicate, and we can see that it is mostly the same. So the treatment didn't lead to a loss of degree of order, preserving the structure of the material, which is good because we use such a high quality sample. The DGA curve, the differential one, in the treated material, it consists of three main peaks, and the treated one has the same three peaks, but it has a new one at 170 degrees Celsius, which might indicate release of sulfur from the sample. And to better study the sulfur inserted, we did a sulfur XPS of the treated material, and the XPS gives us a percentage of sulfur of 0.2% atomic, which is quite good. And we have two peaks. The lower energy one is the thiol peak, and the higher energy one is the sulfonic acid peak. To better study its interaction with gold, as I said, it sticks very well to gold. And unlike the pristine material, we deposited it on gold and did the XPS, and we obtained the sulfur gold bond and the same carbon sulfur bond. And so I compared this to the literature to confirm, and we can say that the graphene is bonded to the gold through the sulfur atoms. My friend did some applications on voltammetry that I won't show, and it shows a much better electric contact. And we investigated the zeta potential to see why it disperses so well. As you can see, it is considered that it discharges above 20 modules of charge, and so the untreated one is mostly uncharged unless it is really alkaline, while mine is negatively charged after about pH 3.5 to 4. And this explains why it disperses so well in water. And we attributed this lowering of the zeta potential to the protonation of the sulfonic acid group that, as I said, is a strong acid leading to anemia, which has negative charge and leads to this effect. To better study the thiol groups, we applied the Hellman method. It is a selective method for thiol and spectrophotometric, and we did the variation with treatment time. As you can see in the graph, it increases up until about 2 hours of treatment and then decreases. And as I said before, the thiol groups are important to interact with metals under further functionalization. And I have a proposed mechanism. I did some research on radiolysis and photolysis of potassium thiocyanate solution. Those processes have the characteristic that it produces hydroxyl radicals like plasma in the presence of water, and they detected both these radicals, the sulfide radical and the sulfonyl radical, which can be detected using EPR, but we still didn't have time to do it. And here's the proposed mechanism. Those radicals are both naturally present on edges or can be produced by plasma, and it neutralizes with another radical, leading to a functional group. And so, to wrap it up, the pristine graphene was functionalized with sulfur inserting both these groups. The pristine structure of the material was preserved, and the material will be applied in future works. I'd like to thank everyone for listening to my presentation. I'd like to thank those providing the lab where I work, CNPQ for the financing, here's the data, Unicam for the XPS, Caesar for the zeta potential and the TGA, Professor Jamil which gave me the reagent to measure the FIO. I'd like to thank Luis Octavio and Nito who is here. We are my advisors, and Chris which is my IC which helps me a lot in the lab. Thank you.
Thank you very much for the presentation.
I also have cut slides if anyone is interested.
Yeah, I saw you have at least 15 slides more, something like that. So, do we have any questions in the room? It's late. I have a question for you. So, what's the next step if you want to? You will continue this work, right?
Yes,
So
we are at a very early stage. So I just finished the multivariate analysis to see which process variables are significant to get more functionalization. When I have this new sample, I'll try to make it stick to gold and then apply the click chemistry reaction to insert various functional groups. There are many possibilities. I want to try catalysts, sensing of metals, and other things. I also distribute my samples for anyone that wants to try to do something. I have approximately 1 year to do as much as I can. But the click chemistry ones are the main way.
In your presentation, you told us that for the sulfurs, you use was a potassium-based molecule, right?
ASCN.
So, have you saw what happened with the potassium inside? What happened? You remain in the solution?
It is a salt. It dissolves very well and stays in solution, but it produces a strong sulfur smell. So I think the plasma breaks it down. It produces many unknown species, and it is a huge puzzle. And I'll have to pick the pieces up. But I have the radiolysis and photolysis to begin with. We already bought the NPR to do the NPR, but it is an unknown chemistry. Nobody knows what happens exactly.
So, I don't know if you understood well, but did you analyze the liquid residual after the treatment?
Yes, I dropped iron in it to see if there's still thiocyanate, and there's a lot of it, and we plan to analyze it to see what can be found inside it. But we need ionic chromatography, and ours is broken, but I pretend to analyze it.
Thank you.
From the literature, I can say that maybe sulfate is produced, and maybe H2S, disulfide, even sulfur. Some of the liquid samples, if you let it decantate, it gives a bluish hue that may be from colloidal sulfur.